So first, you need to enable the sound library. So processing makes this really easy for you. There's a little button, little toggle that you can click under the libraries in your editor settings. They'll automatically include the sound library for you. If you were working in P5.js on the P5.js editor, or you were running it locally in your own web server, you would have to go find p5.sound.js and put that into your directory and use an include tag in the HTML portion of your sketch. Luckily, we're in processing. We don't have to deal with any of that. You can just click the toggle and it works for you. In the Java version of processing, you'd have to go through the package manager and download an entire package and have it installed in the directory of your sketch for it to work. So we're in a pretty good spot here. You click the button. There's lots of things you can click here. Some team, there's actually 2 teams that are using the webcam. We have teams that are already using sound and it's working quite well. There is a game engine in here. There is multiplayer engine. Heck, there's a machine learning. There's a TensorFlow, TensorFlow API, a TensorFlow pass-through library that is in here as well. So there's lots of stuff going on. Now, you can use other options such as Open Sound Control Protocol to communicate with third-party apps. So these are for your the music engineers in the audience or the music artists, because you can hook your sketch fairly easily to MaxMSP and Pure Data. How many of you have used Max or PD in this class? Oh, just one? Okay, you're in for a treat once you get into some of these audio engineering classes. This is like visual programming for sound. It's really neat. I like to think of it as sound shaders because I learned shaders first and they kind of have a similar flow. So third-party libraries are also available to do alternate sound things such as PS Live Media and Jibber. So there's lots of ways to do sound, but the default implementation of sound is perfectly serviceable for the purposes of this class. I just want you to know that more things exist if you wanted to go a little deeper. Now, processing and P5, they're incorporating sound. It's a work in progress in most cases. In fact, I had to refactor all of the sound code for today because there was a huge update in December for the P5.js library. So all of my materials before we had to rewrite and put in because the library and a lot of the ways it was factored had changed. So all the different functions I'd need to call and all the different variables you need to use were a little different. So when you're looking in the world for sound examples and they're not working in your code, you may need to look at the freshest documentation, which you'll find on the p5js.org, where we see all of our documentation. All right, so you need sound files, obviously, but that's one. So your MP3s, your WAV files, etc., OGs, Vorbis OGG files, all of those work. I couldn't get AIFF files to work. I was playing with it today, so that is something to check around. So that means your iTunes files will have a hard time being used here. There's audio in, which you can use with which audio in is your microphone, right? So I'm speaking on right now. It's an audio in device. You have oscillators, or tone generators, and these are like noise colors: white noise, brown noise, blue noise, pink noise. All these things you've heard of. All those like listen to this soothing tone for your ADHD on YouTube. That is on there as well. But you can generate those tones with a tone library. So just like you would click to include sound, the sound library, you can do the same thing with tone. And it will generate lots of interesting tones and white noise things for you. And so you can look at that library here at tonejs to GitHub.io, which is the official place where the code for it is stored, and you can find some documentation there. There's also oscillators. So you can get sine waves, solid waves, square waves, pulse waves, all the good little oscillators that we use for our chip tunes and for synth, you can access here. So oscillators are part of the P5 sound base library, and you can use them with p5.oscillator, and there's various functions and data structures in there. Then we have filter effects. So there's high pass filters, low pass filters, reverb filters, band filters, the whole shebang, lots of filters for you to use. And you can get to those in the documentation. They are also part of the core sound library. So lots of stuff to work with. So simple example. Make a ring variable. We're going to load the sound to ring, and then we're going to play it. Let's check out the sketch. Which amp? Basic sound demo. The code that we just saw. Let ring. We used preload with sound. Set up, mouse clicked. So you don't see anything until I click the mouse. Ooh, let's make sure we have the sound go into the right place. There we go. Like someone really needs to get into your house. Simple. And all that I did was added, just like we did with audio files, or with image files, I simply added a WAV file called Ding Dong and loaded it. You can do more things. Now I hope this works, because now I'm like splitting the microphone between two sources. We'll see what we have going on here. But what we're doing here is doing a little analysis of the incoming sound from the microphone. So a few things to look at here is creating canvas, making a background, making a new amplitude class, which is going to look at all the sound that's in your sketch by default. You can get a specific sound files if you'd like. But as it's played and as your sketch is generating sound, it will find the amplitude of the sound for you. And we're also putting an audio in device. Let's just go to the sketch, a little easier. Sound input, there we are. So there's the amplitude we just talked about. We're also getting a new audio in object, and we're calling it microphone, and we're going to set it to start. So what's great about here is audio in. This is something I'm confused about the new version of sound. You used to be able to give it an integer number, which was the ID for a sound device on your machine. Now it doesn't seem to take an integer anymore. So it worked. I need to figure out the nuance why. If you need me to figure that out for you, happy to. We're starting the microphone, so we're accessing the audio stream, and then we're setting what the amplitude is looking at to be the sound stream of the microphone. Then what we're doing here is we're putting the background to black, getting the amplitude level, or the volume level of the sound coming through the microphone. Setting fill to aqua, we're printing out that sound volume, the string version of the sound size that we're getting from the amplitude. We're making it a little bigger, setting a fill color, and using that in an ellipse. So let's see what we have. Oh, sweet. Hello. Hi. Hello. How are you? It's kind of fun. Does anyone want to play? Does anyone come up and try? Okay, fine. So that's... Yes. Okay, let's everybody shout. 1, 2, 3. Ah! So we maxed it out, right? So we could make that a little smaller. You can see the actual number value that's being generated right here. So, not too bad. It's getting the amplitude of what I'm saying. And it looks really neat up there, where the projector is coming through the dusk screen or whatever that the window is up there. All right, so that's getting the amplitude of our sound object. With not a lot of code. There's a little bit there to figure out, but it's nothing past your capabilities at this point. I mean, there's a lot of hard work being done on your behalf by the sound library. And they offer a lot of flexibility. And this will be our last thing for sound that we're going to cover. And this is the C Sound project. So this one, I think it's better that we just play it, and then we'll discuss it. Test. Check. Hello? So the top is a waveform analysis of the incoming sound. The middle is doing beat detection or peak detection on the audio coming in. Like if I was good at beatboxing, like the guy from Police Academy, it'd be awesome, but I'm not quite there. There's some very good beatboxing TikToks. The bottom is amplitude, and we're just using that to give us a little mouth, a little sound mouth. It kind of matches my mouth. It's kind of fun to talk and then watch it go. 7 years ago. That's the only public politician speech I want to say today. So here we are. But you can also use all this with sound. So what I'm going to do now, or with a music clip, I'm going to set the active sound to be the music clip. And I'm going to set it to play. Does anyone know the song? Yeah. Exactly. This is Summoning Salt classic. Rainbow Road by Tony Paxton, I believe. It's in the Rainbow Road album called Soaring.
I think.
Yeah. So there you go. Speed runs. We'll see more of those today. So that was Summoning Salt, a documentary filmmaker that makes a lot of really interesting YouTube videos about the speedrun community and speedruns over time. And those are video game speedruns. So what we're doing here, it's much like before. We're getting a sound. We're getting the soaring.mp3. This was the AIF file I had before. I converted it into an MP3. And we're giving some variables that we need. So the music clip we're playing, the microphone that we're talking through, the beat detector, the amplitude detector, and the waveform. So all those three qualities that we had over to the side are there. Let's just go ahead. While we're talking about this, you can actually just see it on the side. And no, wait, we actually want the microphone. Pardon me while I fumble the keyboard. All right, so what we have here, the music clip, microphone, beat detector, amplitude. So beat detector is the yellow ellipse in the middle. The amplitude is the thing that's giving the data for the mouth, the grayish white mouth at the bottom, and the waveform is the thing at the top. And so we are setting the beat alpha, so that's the fade value of the yellow circle. The alpha decay, how long it takes that yellow circle to decay from its alpha value down to 0. We're getting a number of samples that we use for this line. And we are getting, we're making a samples array, and we're also getting a fast Fourier transform, which is the thing that's doing a lot of the analysis for us. Does anyone know what Fourier transforms are? Fourier transforms. Okay, that's math. Maybe we'll get there. Making a canvas, turning off the stroke, getting our microphone, getting a new fast Fourier transform, getting printing out the music clip so we can see what music we're playing. We're starting the microphone. We are setting the active sound to be the microphone sound clip. We're getting a new beat detector from Peak Detector, and we're making sure it runs between 20 hertz and 20,000 hertz. And we're setting a logarithmic threshold of what it counts as a beat, threshold for a beat, to 20 from the default of, or 0.2 from the default of 0.35, and we are setting the sort of like frame length of a beat. So there's a lot of stuff you can play around with the peak detector. Amplitude's a lot easier. We're just getting the amplitude detector and we're attaching it to our sound clip. So in draw, we're setting our beat alpha decay if there one exists, like we're making sure if there is a yellow circle, we're decaying it. If the beat is detected, we're setting the alpha to 255, meaning it's fully opaque. So every time I talk or say a word, notice that the yellow lights up. It's detecting my speech as a beat. It's very kind of it. And we're setting the alpha to 255. We're making sure first that we call the FFT.analyze, which actually does its internal analysis of the sound. And then we are updating the beat detector with that analysis. And we're saying, hey, was there a beat detected? Then we are setting a call fill color with the beat alpha, and we're drawing the yellow ellipse. Now here we are drawing the white mouth, and that is simply taking the amplitude, the level of the amplitude that we've detected from the sound clip, from the incoming sound source, and making that be the Y size, the height of the ellipse. Then finally here, the more complicated one is where we're getting the waveform from the fast Fourier transform from the samples. And that comes by, in default, 32 samples. I said 80 above, but didn't put that in here. I thought 32 looked a little better. So you actually see it looks a little pixelated. You can see the gradations. You see each of those different bands. And here we are simply, for each one of the sample lengths, so each one of those 32 bands that we compress the sound into, we are simply drawing those and given the height of that sample size. All right, so there we go. You understand it all about as well as I do, I'm sure, at this point. All right, any questions about sound? So those sketches are available, are not available, because I forgot to click this button. Now they're available. So feel free to use those in your projects. All right. Any more questions about sound before we move on to game feel and the jump? We're not going to actually talk about too much about the jump today, mostly game feel. All right, what game is this? No one's played Needhog? It's a little, a small indie fencing game that won quite a few awards, and mostly because it feels so good to play this game. Right, from the dashing to the dancing to the fencing to the massive amounts of neon pixelated blood, this game was sort of like a kinetic joy to play. And it's because they had the game feel just right, this abstract thing that we sometimes talk about, the juiciness of a game, the responsiveness of it. You can see another good example in game feel in Destiny 2's gunplay, which is immaculate. So this is how responsive. What sort of emotions and feeling do you get when you play the game? How does it feel to play it? Does the input controls and the way the characters move match each other in some visceral, fun way that adds to the experience when they're used all together and seen as a whole? So let's unpack about that today. So first, basing a lot of this from Steve Swink's Game Feel book. Really interesting book if you're a game developer or someone who wants to deal with anything interactable, and I include any UX design in this. This is a great book. This is a great read. So Swink breaks down the world into real-time control, spatial simulation, and polish. And so you can see by there being Civ 4 and Peggle and StarCraft being references, you can see that this book may need a new edition sometime soon, but all the core stuff still stands in it. So when you have something with good real-time control, that's great. If you have some sort of spatial simulation to it, like Bridge Builder, where the size of the thing on the screen is not nearly there's some abstract quantity within spatial relationships, it's only 2D in Bridge Builder, you can see that it's in a different category, right? So you can have all these overlaps here. Polish are games that are, where the visualizations and realizations and modeling and sound are all very well kept, like Civ 4, Bejeweled, etc. This all plays into this HCI-ish loop between machine and human. So we go here. This line is the line between silicon and meat. So starting here at the front, we take in what's on the screen, what's coming in through the sound, what's going in through rumble sensors, what's coming in through vibrations and other sort of tactile sensors in your controllers, in your haptic vests, whatever you've got on. You sense this, your body feels it. You take it as input. It all gets sent through nerves to your brain, and your brain's got to figure out what to do with all this information. Like, what is it interpreting that screen as, right? And then you eventually figure out what's going on. You make an internal mental model of it. That got loud. Sorry. Internal mental model of it. And then you have to make some action. Do something. Move a finger. Press a button. Shift left. Like my grandma. Run the controller when you jump. So all of this are ways that we can interact with the digital. We now have our meat hooks pressing buttons and sending digital signals through a controller, joystick, Wiimote, phone accelerometer, capacitance touch screen on your phone. And that's all sent as information, just like key pressed and mouse X, mouse Y, mouse press, mouse drag gets sent to your simulation running on your machine. So we are colloquially calling this in this area is the processor, but you know the processor is just one part of a computer. And then the processor has to figure out what to do with that input. How does it configure its own internal bits? How does it send graphics to the graphics buffer and sound information to pulsing magnets and coils to generate sound waves that get picked up by your ear? So that's what we're doing a lot with P5, is actually reacting, configuring what we know in the input to something on the screen that we care about, that we think will provide the experience of our simulation to the player. It will configure the screen, the sound, any other output devices, all the surface layer information that we then send back to MeatSpace. But that's not all. That's just the inside of this bigger loop. There's all sorts of other conversations going on here. So here we have our basic loop that we had talked about before, sort of compressed here. But there's a little more to it, right? Here we have things like the avatar of the virtual world. Does it matter whether you're playing a disembodied commander in a real-time strategy game, or are you playing Gordon Freeman from Half-Life, or are you playing Mario, or are you a Pokemon master, right? All of that exists within this fictional context of the world that's sort of embedded within that simulation and is presented to you. All of those polished rules, context, metaphors, responses, input, all of this lives inside of that sphere. But then there are other things going on, like outside your perceptual space. We have input. We have the actual console or computational device running the scenario, running the computation. That's sort of like outside of this perceptual field. It's sort of like this thing that's doing all this work, but you don't really have in your mental model as you're dealing with the surface level pixels and sound coming at you. And then we are in the space also of the real world. Unfortunately, the real world exists, and there are social, political, economic, cultural, family, societal factors that you sit down with as a human being, as a whole person, every time you play an experience. You come to this classroom every time you play a game, every time you press play on a sketch and move your mouse. All of that exists within this design space. So you also have this level of having you as a player having a conversation through a digital artifact with a designer who designed something a long time ago. And you're now interacting with it. So there's all these different layers of thought and communication and nuance here to pull apart. And Gamefeel is one small slice of this larger, more interesting production of human in silico. I don't really need to talk about that a whole lot. I think this is fairly obvious. The metaphor that you're playing with, the response that the machine makes to your inputs, the rules that govern the game world, mechanics, systems, dynamics, etc. We have the context. So what are these little blocks? What do they mean? What do we know about them? the polish, how well does the jump look and feel, and then we have input, which is the input scheme. You press B, Mario jumps. Perception and motion. This is probably one of the more interesting things to take away from this game feel UX UI design space. And this is the 3 perceptual areas, tasks that the humans go through when they react to the world. So the first is perceptual. How long does it take those photons to hit your eye for those cones and your eye retina and everything to send through nerves to your brain to get mapped into your brain somehow? And then how long does it take that information after it gets to your brain? How long does it take for your brain to turn these photons into, hey, that's a screen. On that screen are pixels. These pixels contain blocks, characters. You end up understanding and parsing all of this information into entities, into things that you perceive, that you can reason about. And so that gets you all the way to here. Then after you have all these perceptual things in the world, you know what the blocks are, you know where the Goombas are, you know where the coins are in Super Mario Brothers. Then you have to decide, what the heck am I going to do? How am I going to react to this? Am I going to keep moving forward? Am I going to jump? Am I going to move? Am I going to maintain what's happening now? Do I need to make a change? Then, after you've decided what you're going to do, like press jump or continue running right, then it takes another 70 milliseconds for that signal to pass through your nervous system and activate your muscular system, in effect, to press a button. Right? So now, we now have this window of 100 plus 70 milliseconds. Each one of those are thousandths of a second. So you have 0.17 of a second of this reaction time. Like those little driving simulators that they usually make you take in high school when you learn like a bit about driving, and they're always like really hard, and like little squirrels and kids jump out in front of you and you have to like stop in time. Like these things are kind of infamous. They play around this time. They actually make it much faster than humans can react to make a point to you that you are not omniscient, that you will make mistakes and some things are out of your control. And everyone's a little different, right? I know some fabulous people, a lot of musicians in particular, that these are very much smaller than how I exist in the world. There are people with faster reaction time than me, and there are people with a lot slower reaction time than me. So there's a lot of play here. Like those games where you like put your hands on each other and you try to slap each other's hands. Like that's another one of these processes. The faster you can do this, the better you are at that game. To put this into context, that sort of like looks like a very mechanical process, but we're actually doing this continuously, right? We're not like thinking frame by frame as humans. We're much more meat than that. We are analog. So, there is this tasty muffin. So I've decided I want that muffin in my hand. So I have this intent to get to the muffin. So what do? Well, I go through this constant loop of comparison, action, and perception, monitoring reality to make sure it matches my intent to grab the muffin. And so first you have this like lunge at the muffin. We're going through this almost 1 second muffin grab. We're a quarter of the way through, and now we're halfway to the muffin with only a quarter of the time. But then this muffin is delicate. We want to make sure we grab the muffin successfully and just don't like completely clobber the thing as we move right through it and destroy it. So we slow down in a very organic way. Much like those animations we saw in The Illusion of Life, there's a little bit of move and then slow down and then anticipation, and then you grab the muffin. Delicious. Right, so you constantly monitor what's going on. Perhaps you slip, perhaps someone is rude and steals your muffin right at the last minute. Someone just slaps your hand out of nowhere. So how does this relate to what we care about with frames and animation, with frame rates? How do we turn this little bit of information that we've talked about into something actionable? Well, let's start at the basics of animation, right? Little frames of animation, a flip book. So how many pages per second of a flip book do you think you need to make it look like animation versus a bunch of little pictures? How fast does it have to be before your mind has the illusion of motion? Any thoughts? The answer is right on the slide, right? I'm not being tricky here. 10 frames per second. Huh. What's a tenth of a second in milliseconds? 100. Oh, so perhaps when things are moving faster than our perceptual cycle can handle, we start to do motion blurring and motion bending and see things as continuous instead of discrete. I think that is very much the case of what's happening here. And you can have this interpretation here too. This is the sort of like effective takeaway of those cycles, where things that happen under your the average perceptual time, seem instantaneous. You didn't have time to process that motion. It happened within under a tenth of a second. To the human eye, that's almost like faster than you can process. But then we have this ability to think about what's going on, to form a strong mental image of what's going on. That's another 70 milliseconds, right? And so in between that time where where things look like they're instantaneously happening versus when you think about it and can form a good mental image of it and form actions for it, there's this golden spot here of things looking very snappy, very interesting. Action feels not too instantaneous, but not too slow. This is the sweet spot. So when you're thinking about reactions, like something hitting something else in your games or things touching and moving based off user input, having them happen right away is typically not the best move. If you add in a little delay, things look a lot more alive and a lot more weighty and a lot more real because they're moving in ways that we perceive reality. But then once you get past 150 milliseconds, 200 milliseconds, 200 milliseconds is 5 FPS. That's kind of unplayable, right? So once you get to this area, things are too sluggish. And once you get, for most people, to 4 frames per second, it looks like it's broken. There's no longer, like you have now completely passed away out of that motion, out of that like suspension of disbelief, that ability to see frames as something smooth and moving. Once you get over 200 milliseconds, you pop out of that and things start looking like sequential pictures again. Prince of Persia, the original Jordan McNamara game from the 80s. Now, this one was one of the first to have a really fast animation system, and it was on like the fancy fast PCs of the day. This wasn't like your arcade Pitfall game where we saw the one thing that looks smooth and awesome was the rope because it raced the beam. Well, a few years later, we had Prince of Persia, which featured a 16 frames at 30 frames per second animation time, and this ended up being 0.53 seconds for an entire walk cycle. What we're seeing up here are all the frames that appeared in less than a second. Now all of a sudden we're dealing with something that has real motion and something that was moving pixels and something animated that quickly. And so this was quite groundbreaking for the time. Prince of Persia, the hop felt really good, the jumps felt down. There's even like the hopping animation, which people like really raved about, going from one level to another in this 2D exploration game. It took 150 milliseconds. 150 milliseconds on the sluggish end of the sweet spot. So it looked weighty and hefty. It's something important, but still reactive. So this is a really interesting one. We're here at this world where we're doing 32 frames per second, or 16 frames at 30 FPS. So 30 frames per second, which is, 0.33 milliseconds per frame. Looked really good. So when you're doing the interactions, you should aim somewhere between 100 and 150 milliseconds for response times. What's this game? Super Mario Brothers, right? Why do you think I have these two lines drawn here? Yeah.
To track how the camera shifts, so it's based on the character, but it moves when it moves forward, but then otherwise it stays in place. It's tracking the character.
Exactly. So there's a little more nuanced stat, which we'll talk about just a little bit. So this is infamous. There were two things that made Super Mario Brothers really click, that made it really feel much better than the other games. One was this camera movement. The other is the fidelity of the jump. There was nothing like it at the time. Now, the camera here, when you get to that line, the left thin line, when you're between that and the thick line, the camera moves to the right. But it only does so at something like 80% of Mario's movement speed. So you have this little acceleration zone with perceived acceleration where Mario's moving faster than the camera. And then when you hit that right side, the camera is pegged right to the center of Mario. The camera never moves to the right, but only has this simple acceleration, this speed up zone and push line algorithm. And that made the scene transitions look really good, as opposed to being pegged right in the center of, having Mario always in the center of the screen. And at maximum speed, it takes Mario, just about 3/4 of a second to go from one edge of that through the speed up zone to the right edge. Right, so that feels weighty, right? That feels like it still has some motion that you perceive, but it also has an acceleration quality to it. The curve of the motion, of the speed over time, is something quite interesting, and it's more fluid, which sort of like belies its 8-bit nature, low frame rate, blocky pixels. But all the motion and the physics and the movement are really good. In fact, like for every pixel on the screen, Super Mario Brothers actually has sub-pixel values. So there are so the actual location of Mario is 32 times more precise than the pixels on the screen. Right, so there's all sorts of interesting stuff going on here that makes this an artifact that we care about. All right. So that also brings us back to another quality of this, input. All right, what are these two things? A D-pad, WASD. Have all of you used these before? This should be pretty common. All right, so they both do basically the same thing, right? Up, down, left, right movement. What's the difference between these? What can one do that the other one can't? What's one good at that the other one is not? Please.
You can press multiple keys at once with WASD.
Yes. Yeah. Oh, same thing. Right. You can do multiple times, but particularly you can do oppositional things. You can press A and D at the same time, and W and S at the same time. Although you should never use the S key. That's a bad PvP. What does one do better than the other then? So we've talked about what the keyboard can do that the D-pad can't. What's the D-pad good at? What does it facilitate more than WASD? Have you played Street Fighter? Yeah, exactly. You can do like a quarter of control. You can do left, down, right in a swooping motion with your thumb. Yeah.
Like the quarter circle motion?
Exactly. You can shoot all your Hadoukens.
Yeah.
Exactly. You can do Shoryukens much easier with all this, yes. All the classic fighting game things you can do much easier with this. Now we're in the days where we have thumbsticks. And those make life a little easier, although it's kind of hard to get true down on a thumbstick. True up, it's hard to move really precisely in any direction. So you need to do some post processing and have some zone snapping. But we have good things here. We can use these. Thumbsticks, they're really good at rotational things. They have more movement. So here we have 4 buttons, right? 4 zeros and ones, either up or down. So that's, 4 bits of information. Here we have, with thumbsticks, we actually have a continuous circle where you can be sort of with a decimal, any point within -1 or -1 to 1, -1 to 1 in a circle, right? So you can always be distance 1, sort of thinking about our radial conversions. If you remember in the Wayback Machine when we talked about radial coordinates, that's what these controllers are. Radial coordinate systems. They're really good for games like Flow, where you have one to move and rotate in circles. Now, if you look at this, each one of these gives a little bit more information for us to use in our games, in our models, in our experiences. Buttons have 2 states, on or off. The trigger, interestingly, did start out only having 2 states, trigger pulled, trigger not pulled. Successive ones had 4 states, so you get each quarter that you pull on the trigger was a different state. Now they're continuous. The value between 0 and 1, how far did you pull on the trigger, often is mapped to how far back did you draw the bow. So you can do pull the trigger all the way and do a large, heavy shot. You can pull it back a little bit and do a smaller, more precise shot with lesser range, maybe lesser damage. And then we have, so that's, in this case, with this, when we see on the screen, you have 4 states of information instead of 2 like buttons have. But with the thumbstick, we have thousands of states of information. That's only limited by the precision of how we can map decimals into zeros and ones to use in the machine. Then we have keyboard, like mouse. Well, when they figured out that you could use the mouse as the metaphor for the camera planted right in the player's head, and then you moved your mouse around and that moved the head around, that was gold. That really mapped very well into this viewport metaphor of the world. And that didn't happen until mid-90s. Doom didn't even have it. Doom, you still had to move with keyboard. Mouse didn't really have a lot for you there. And then we have potentiometer-based games, like early arcade games, and some of the controllers for the Atari, where you could play breakout loud games, where you basically have that paddle and you stop the ball from going under the paddle and it bounces around and breaks all the blocks. Well, controlling the paddle with a potentiometer was kind of neat. You want the paddle to move right, turn it clockwise. You want the paddle to move left, turn it counterclockwise. And so it just has how fast it's moving in which direction. So a 0 to 1 in speed, -1 would be counterclockwise, or the negative numbers would be counterclockwise motion, and the positive numbers would be clockwise motion. Now, all of these have a different set of input sensitivity. So buttons 0 to 1, we have D-pad and keyboard close to each other, next to triggers, next to potentiometers. Then we have thumbsticks, then we have a mouse. What else could we have? What are input devices that give us more information? Yes.
Something like the Wiimotes?
Yeah, the Wiimotes have a ton, right? They have I believe they have a 3 degree of freedom accelerometer plus all of the buttons.
Something like that.
Yeah. Now accelerometers are great. You have like these 6 degree of freedom accelerometers, which are basically a magnometer plus the accelerometer, all packaged into one little bit. So a little spring, a tiny like smaller than a millimeter spring, and then you see which way the spring's going, and that's which way you're moving things. Like you do, it keeps a sense of momentum. And then you have magnets which sense north, south, east, and west, and can give you more cardinal directions. And up and down to some extent. So that's a lot. What else? Yeah.
Like those arcade racers where you have to engage with like pedals, and then you're also using the steering wheel.
Oh yeah, the arcade simulator, the racing simulators, and then like you have the cockpit simulators.
Yeah.
Like people have these sweet like Microsoft flight sim rigs in their house that like could span their entire garage. Yeah. What else? Where'd you put VR on here? Blue sky for me. What else do we got? What's we know VR's at the end here. What's past the end? I've seen inputs where they have vests that imprint braille on your back. That's more input space. Give me some sci-fi. Give me some Keanu Reeves, yeah?
There's a device that kind of like reads brain noises mostly. essentially like comparing like the like brain activity from between focused and unfocused.
Yeah, there's like EKG devices, ECG devices. Yeah.
Those and those like it's usable in like children's toys too, like very basic ones.
Yeah.
So those can be very sensitive.
There were meditation games starting as early as late 60s and early 70s, computational games that you played with one of these monitors for to see how like smooth you could get your brain patterns, and they map that into meditative states. Like what about motion capture? Right? Your full body is now a controller, now complete with fingers. But we have more blue sky things. What about a neural interface? What about the holodeck from Star Trek? What about jacking into the Matrix? Right? We have the potential to go very much higher on the sensitivity of our devices and make games that act correspondingly. And our ability to input our actions well into a game is something that kind of holds us back. Like, I don't know how many times I played like, you know, one of the, like some of the Call of Duty games, and you can just like basically beat the entire game without touching the controller. Right? It doesn't actually take a lot for you to actually play these games. The more input sensitivity you have, the more you can work at the level of the simulation in the game to play it and get more of a sense of flow, a sense of feedback, a sense of place and space, a sense of game feel. Right, so this is interesting. Some of this may appear on the final, right? Like how many, like what's controller sensitivity, which one's more sensitive than the others and why, which one provides more information and why. So you can check these out. These actually have different degrees, different axes of information and input ranges and values. And what we're trying to get here is a sense of flow. We want to be organized within this, within our ability versus boredom. Like what can we do that's challenging versus what versus what creates boredom or anxiety? How can we stay in the intermediate spot between these and get a sense of flow in our experience where we lose track of time and get into play and nothing else exists in the world? This is just for your information. I will not expect you to like read this for the exam, but this is like an explanation of a few valence of these input devices and why they're useful and interesting. So those of you who are more, who want to get deeper into this may find this interesting. All right. Attack, decay, sustain, release. Let's operationalize some of this. So this is the ADSR envelope. This is coming from the notion of sound and sound reproduction with instruments. We're going to map that to motion in games. So first we have the attack, where the initial sound hits, the plucking, the strumming of a guitar string. Decay, the initial burst of energy goes away, and then you have sort of like sustained note for a while. And then finally, the release, where all the energy bleeds out of the string. This is what the envelope for guitar looks like. String plucked, got the attack, that decays a little bit, then we have sustain, then a slow release where all the volume goes out of the guitar. This is a pipe organ. Press the organ, opens up a valve, wind goes immediately through and starts blasting. So it doesn't take long to go from no sound to full sound, and it'll stay full sound as long as you have the key pressed. As long as you still have the people pressing the bellows in the bottom of your cathedral, then you release the key, closes the valve, the wind energy dissipates quickly, and the volume goes away, of course, with the corresponding quickness. This is roughly what a Super Mario Brothers-like character would look like. Notice there's no decay here. You press right on the controller, you'll start running, and then you'll get up to a sustain speed where you'll keep going until you release the controller, and then you skid to a halt. Make sense? So instead of having sound here, now we're mapping motion over time. Have a great day. This is Mario before Mario was Mario. Who was Mario before Mario was Mario? Does anyone know? Yeah? Jumpman. Yes. Donkey Kong, exactly. Moved very differently than how Mario does in Super Mario Brothers. He was basically a pipe organ. Flighty, light, motion was very fast. You press the button, instantaneously moving in maximum speed in that direction. You let go of the button, almost instantaneously stops. You know, that's not super good game feel when your weighty plumber fighting a Donkey Kong like feels like he has the weight of a feather. Now I'm going to give you some of these. The dreaded interpretation time with discussion. All right, how would this one feel? It takes almost a second, a little over a second, to get up to your sustained speed, and then a linear release. How would this feel? And what type of entity would have this motion, this curve, this speed? I'm going to just give a moment to let some other people think about it as well, and then I'll call. What do you think? You can synthesize what we know so far. Hey, notice there's 200 milliseconds here. That could be important. What do you think? Yeah?
It could be, kind of depends on what kind of environment the player's interacting with, because it takes a considerable amount of time to, it's like a noticeable amount to get to max speed. If you're in an environment where it's constantly trying to take your speed down, it could be frustrating over a long period of time. But
Yeah.
it's something like, I guess, like, thinking of like as like a kind of a car would kind of have this kind of curve.
Yeah. Perhaps some sort of vehicle could have this curve. Yeah, that's all very good analysis. Yeah.
I was just gonna say, like, likely for like a character model, it's probably like a sprint, or a, or like I mean, like in sound, probably it would be like a rec, or like that build up, like revving an engine sort of thing, till it gets to that sustained point. But
Yeah, there's a couple interpretations that could be here. Anyone else want to add? Yeah.
I think if this is like the player character, I thought it would be like a charge attack.
Mm-hmm.
There's a really long like wind up, and then the animation plays, and then that's it, and then quick to stop.
Yeah, that very much could be. Like you could map that to a game mechanic more than just motion, absolutely. So this is more like a dump truck. Sisyphus pushing a heavy boulder up a hill, getting momentum in the system, something that takes a long time. Notice that there's no perceptible action until over 200 milliseconds have passed. Given what we know before, this feels real-time broken. You press right, and nothing happens for a conspicuous amount of time. And then it slowly starts churning and churning and churning until it gets up to speed and then has sort of like a grinding linear release. If you were going to say, hey, maybe make this like an F1 vehicle or NASCAR, this would be different, right? You'd have a fast acceleration off the gate, and then you'd have like sort of like an asymptotic slowness that goes to max speed, which then you could sustain for a while, and then you could have some sort of braking release. So this is something heavy, like unfathomably heavy and slow. What about this one? Yeah.
I imagine it as kind of like a character holding a bag, so their first two, if they're running that way, the first two steps are really fast, and then the bag weight catches up with them. So you're still accelerating after that, but you now have the other weight until you get up to max speed, and then you can stop kind of as you please.
Yeah. This one's that. So you've described a situation that maps to this abstract pattern of a quick punchy start, like this initial acceleration getting up to like half speed is fast, and then it takes a while for it to really get up to a sustained maximum, right? This you often use. This is a classic racing game. One, I sort of teed this one up just a little bit. This is a classic racing game example. Burn quick off the line, and then takes a while to get up to maximum speed. Like Captain Falcon from F-Zero. What about this one? Tasty. This is organic motion. This is grabbing for the muffin. This is the fast muffin. You have, you're going half the speed towards the muffin in almost half the time, very fast acceleration, and then you slow down as you get close to the muffin and you grab it. Like, this is a classic organic motion of walking, running, moving. What about this one? How do you interpret this? We've looked at this. This is the organ. We know the Jumpman was this. So what sort of qualities does this impart? 1 then 2.
I was gonna say, this is like Roadrunner just going like, whoop, like just kind of ending up like, it's kind of like, I guess like it would embody some sort of, like how you were talking about, like some sort of just fast one-to-one, like point A to point B without much articulation.
Yeah, very Roadrunner. And then it'd be squash and stretch at the end,
Yeah.
right?
I think it would feel very slippery because it's like there's no gradual stop. It's just basically stop or go, which might lead to a lot of like misinputs kind of thing.
Yeah, it's too twitchy, right? Very twitchy of a play experience. Anyone else? Yeah.
It reminds me of when I played Fallout 76.
Yeah.
And I press the key to run and it's immediately go, and then when I lift off from the go forward key, it immediately stops.
Yeah. Well, how did that make you feel? Like, what was your experience when you did that? How did you feel of like the heft or the weight or the motion?
I didn't really like feel anything. It was just like, oh, okay, here we go. Like we're running full speed automatically, just at a press of the key, and then we immediately stop. And I'm like, okay, like I guess it did feel something because it took some time to get used to, especially like we're running around enemies and stuff.
Yeah.
Monsters. But yeah.
Oh, that absolutely makes sense, right? So what we have here is instantaneous stop and go, which can either be something feather light or something like supremely powerful. Something that has heft and weight to it, but is also overpoweringly strong. That it can move with that speed given its weight. Like a AI controlled spacecraft with something that with like an inertial dampener or something. Can it break the laws of physics? Okay. This one I want to get to. This one was actually a very prominent exploit. This is the animation curve for Counter-Strike's bunny hopping. So in the original Counter-Strike, they wanted for you to be able to move very quickly and feel like you sprinted fast off the line, so they had a little bit of boost and then a decay. Why is this bad? How is this exploitable?
If you keep tapping the button, you can have a higher max speed than intended.
Exactly. As long as you like press the button with a certain frequency and release it with a certain frequency, you can get your max speed to be like somewhere between here and here, right? Which is faster than sustain. So you had all these like stuttering, like weird animations of people getting to places in the maps faster than they could to set up their shots. All right. I ran a little long today, so let's skip right ahead. I'll leave this to you to watch. You can see like what planet Super Mario Brothers is on. It's somewhere between Jupiter and the Sun, given the gravity of Super Mario Brothers. This was a PBS public radio show, so you can watch this. It's kind of neat. It's not long, because I want to get to speedruns. Oh God, we have like 10 minutes. I spent way too long.
Super Mario Brothers any percent. Whenever someone sets a new world record for speedrunning this game, it always makes the news. It's not only one of the most popular and recognizable games of all time, but it also has something unique as a game to speedrun. A key element that makes every improvement to the record a landmark achievement. We'll talk about that. But first, you have to understand that all past records pale in comparison to what we'll talk about today. Last month, speedrunner Nifsky did the unthinkable. Today we'll deep
This is
dive
about a
into
year
breaking
ago.
down
Over a
his
year ago.
accomplishment, a feat so great it's worthy of the title, the biggest milestone in Mario speedrunning history.
Let's go just for a bit.
I've had a hard time getting sponsorships for my videos, so I really appreciate your support by subscribing
Like
or
and
on
subscribe to
Patreon.
Cosmic, right?
All
Luckily-
right, today we're
blissfully
going to
short.
talk about the significance of this speedrun. What sets it apart? What sets Super Mario Bros. Apart as a speed game? How did we even get where we are today? How many frame-perfect tricks are in this run? What is the future of the game? I'll go over all of that, share some unbelievable statistics, and more. First off, you need to know why this run is a big deal. Ever since I got into speedrunning in 2011, I always heard people remarking that the world record in Super Mario Bros. Was perfect. Despite the record being improved every year for the past decade, a lot of people are still under that impression. Well, this time, it finally is. Up to 8-4 anyway. This run is completely flawless prior to 8-4, and is the first run ever in history that was. Nifsky's run is absolutely perfect pace in 7 out of 8 levels. This game famously runs on cycles known as frame rules, which limit how fast you can go. It makes the run boil down to doing each stage fast enough to make the perfect cycle, even if the stage wasn't necessarily perfect. But with that fact in mind, every single stage still has a myriad of frame-perfect inputs you have to do in order to get the perfect frame rule. Before 2016, nobody was getting the perfect time on any of the stages. This was
I'm going to
mostly due
show
to the
you what
flagpole
these
glitch. By clipping
frame perfect tricks are.
Speaking of numbers that don't tell the full story, let's talk about frame perfect tricks. In case you don't know, frame perfect basically means you have the smallest window possible to press a button. This game runs at 60 frames per second, so if a jump is frame perfect, it means there's a 1/60th of a second window to time pressing the A button. This is a really common phrase in speedrunning, and one I think is a little too sensationalized. It sounds really cool, but it's kind of a misnomer in terms of describing how difficult something actually is. There are some frame-perfect tricks that really aren't very hard. There are some tricks with multiple frames that are very hard. Some tricks have better visual cues than others. Some tricks are multiple tight inputs in quick succession. Some have a nice rhythm to them, which makes them easier to time. And some tricks are a frame-perfect button release instead of a press. There are so many factors at play that impact how hard a trick is to do consistently. So keep that in mind and don't get too tunneled in on the concept of frame perfect. With all of that being said, let's now look at the number of frame perfect inputs in the run. I'll keep saying numbers don't tell the full story, but let me keep trying to tell the story with them.
I feel you, man. If you've ever wanted 59 frame-perfect inputs in a single speedrun, there you go. And this doesn't even include things like pipe jumps, which can be anywhere from a 1 to 3 frame window, depending on where you land on the pipe. In fact, in Nifsky's run, this jump in 8-1 needed to be frame-perfect for him to survive, so you can add an extra 1 to the counter if you'd like. There's also tight movement needed to make the 1-1 underground fast enough, pushing left with good timing on this clip in 1-2, the jump onto this Koopa to manipulate enemy patterns, and so much more that doesn't fit perfectly under the umbrella of frame perfect. Now to put this run in perspective, here's how many frame perfect inputs are generally required at each level of play in this game. This isn't strictly accurate, but it's how many you would usually do with the most common route for each time. You can see it's just skyrocketing as time goes on, and that trend will continue. Here's how many you would need to get the time down to 454.3. We're just marching our way up the stairs to insanity right now. Finally, to get the perfect 8-4 and an absolutely perfect run all the way through, you would need this.
84 frame perfect inputs.
All to get to 454.26.
We've gotten as far as we have in this game by making setups for Trick.
All right. This is the stats of success rate, of consistency, and total like percentage of run that the Niski had to get through the actual run. So getting to the last level 8-4 only happened 0.3% of the time. So every 300 runs, one got to the last stage on this perfect pace. All right. But there's also more to it. Like the actual physical, like the under the hood mechanics matter a whole bunch here to why these tricks are even necessary. And all of these are computational things. These are things in your simulation, things that we have control over.
That reach for 2.
Thanks for 50. Emotes.
Okay, that was a lot to process. First,
Yeah, enough
how
we
did
didn't
that
even get
hack
to see
take
it.
Mario to the warp zone instead of this coin cache. The reason is simple. To save memory, the game uses only one.
There we go. All right, so this first part, you just want to see what's going on here. I'll turn up the volume for it. And we'll be done just now.
The video is muted.
It's, is it? It is. That is
Process.
for that point.
First, how did that pipe take Mario to the warp zone instead of this coin cache? The reason is simple. To save memory, the game uses only one variable to tell where Mario is going to end up when using a pipe or a vine. As you go through the level, this variable changes to match the correct bonus rooms to the correct pipes. The value changes from the warp zone to the coin room right here. However, instead of using Mario's position to change this variable, the game uses the screen's position. If Mario somehow ends up further to the right on the screen than he normally is, he can take this pipe and end up in this warp zone. This is what we call a ROM warp. The reason this saves time is because it allows you to skip this long animation of the vine coming up that you would normally get. So, this leaves the question, how did Mario end up this far right on the screen? This is where the wall clip comes into play. How did Cosmic manage to get through this wall?
Cosmic being the guy who made the last video.
When running at full speed, Mario moves by either 2 or 3 pixels in one frame. This means that if Mario jumps into a wall, it's possible that he ends up right next to the wall in one frame and 3 pixels inside the wall in the next frame. To counteract this, the game simply pushes Mario back out of the wall. However, the way the game does this has a flaw. You see, Mario doesn't get pushed towards the edge of the wall, but rather opposite the direction you're currently holding the controller. So, if you're holding left, the game will move you to the right, pulling you inside the wall. On top of that, while the game is moving Mario to the right, it's not moving the screen to the right. This makes Mario end up further on the screen than the game normally allows him to be, which is what Cosmic needs to pull off the ROM warp. However, it's not that easy. Walls are made up of individual blocks, so even within a wall, you can stand on a block. If you're standing on a block while partially inside of a wall, the game doesn't care which direction you're holding, it will push you out no matter what. This is why Cosmic jumps a couple times. Once you're far enough into the wall that Mario is completely inside with no parts of his sprite sticking out, then the game doesn't really know which way is the closest to push him out of the wall, so it defaults to moving you to the right and you can start running inside of the wall. Note that your position needs to be just right for this trick to work. Luckily, the way this specific wall is placed happens to be in the perfect position for this wall clip to be possible just by holding right from the start of the level. After getting the clip, there are still many ways this can go wrong. If Cosmic starts running too early, Mario won't be far enough on the screen and the ROM warp will fail. If he runs too late, the trick will work, but he'll be too slow to catch his bus and he will lose one frame roll. If he doesn't come to a complete stop on the pipe before he goes down, the screen will keep scrolling as he's going down and the ROM warp will fail. If he stops too early, he won't be able to go down the pipe. If he stops too late, the screen will scroll too far and the trick will fail. If he misses Divine Block, this happens. In fact, hitting Divine Block has no influence on the run working or not. It needs to be hit because Divine coming out of the block adds one more object on the screen, which forces the game to choose not to spawn the piranha plant in the pipe you need to take, in order to avoid going over its sprite limit and cause a lot of lag.
All right, we'll stop it there. This was to give you a sense of how like the decisions you make in your code and your experiences can really matter to the end results, and just to give you like what are the top level of experienced players, the people who are doing speedruns, how are they thinking about games, and how are they thinking about the mechanics that we put in place. Like every time we make a decision with an if statement, that's something that can be played with, right? It's almost the same mentality that folks use in the black hat and white hat cracking and hacking communities, right? All of this is using the computational infrastructure in ways that are unanticipated. And so you need to think about that when you're making your games, and when you're making your games feel good, like Super Mario Brothers. All right, I will send out an announcement about office hours and give you the list of times or the list of the schedule of our presentations for next week, and some due dates. All that will be coming today. I'll also remove the undefined from the sketch so you can check it out in full. If you have any questions, please let me know. I'll stick around for a minute after class. If not, good luck on your preparations for next week, and I hope to see you soon.